All right, actually, give me just a second. Let me get some more water because my throat is already hurting me. Okay. All right. This type of equation, which is where we have some constants A, B, C, D, E, and F, and we have it like this: ax squared plus by blah, 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 equals 0. This type of equation shows up everywhere in a bunch of different ways. And that's what we're going to talk about for this high level stuff. But the motivation for this is that a lot of phenomena can be described with this type of thing. And so in mathematics, we spend a lot of time wrapping our heads around it. And by wrapping our heads around it, like, you know, we want to be able to understand this stuff. And one of the best ways of understanding a thing in math, at least, is to graph it, to get some kind of visual representation. Like, this is just symbolic mumbo jumbo, really. And we want to be able to basically get our hands on it, right? And you can imagine, well, and what we've seen, I think, reasons why you might want to graph something, how it might make your life 10 times easier to graph something. Like I think one, for instance, I gave you before was if you had, say, a parabola and you wanted to know, for whatever reason, when it's less than 0. And it's like, if you tried to do that analytically, right? Like if you had the parabola y equals, let's say, x plus 1, x minus 4, and you wanted to try to figure out just using these symbols right here. Actually, let's go ahead and multiply this out. X squared minus 3x minus 3x, yeah, minus 4. If you just had this and you wanted to figure out, hey, where is y less than 0, your life would be pretty hard, because you would be like, well, okay, x squared minus 3x minus 4 less than 0. And then you could be playing with this all day. And it would be a real pain to try to do that. But, or if you could graph it, you could say, well, hold up. We have zeros here at -1 and 1 over here at 4. It's an upward facing parabola. And so it does something like this. And so I could tell that y will be less than 0 whenever x is between -1 and 4. And right now, this is still kind of high level stuff, but usually this shows up in a certain context where it makes a lot of sense why you would want to know, when does this occur? And so this is one of a million reasons why we want to graph something. And it turns out that a ton of real world phenomena, not just real world, but also abstract mathematical phenomena, can be described with this type of thing right here. And so you spend a good 2 years just learning how to graph stuff like this. And, you know, it seemed, well, it is a lot of tedious work, and it seems like busy work at the time, but trust me on this, like having this as a solid foundation, like being able to take something like this and get a picture of it, can make your life so much easier, and so on and so forth. And not just graphing, right? There's a lot of things that we do with things like this that aren't just graphing, but we do spend much of our time graphing this stuff. And it turns out that all the other questions that you might want to ask, like when are those things equal to 0? When, When does such and such occur? If I plug in a 5 for X, then what? A lot of that stuff can be answered simply by drawing a graph. And so we spend a ton of time learning how to graph this stuff. So now let's get into what these things are. Believe it or not, you've been doing this since Algebra 1. There's this, what we're going to do is look at different cases of this equation right here. So the first case, and the case that you learn about, that you've been learning about since Algebra 1, is the case where A is equal to B is equal to C, and they're all equal to 0. In other words, the case where you have an equation of this form, dx plus ey plus f is equal to 0. You recognize what this type of thing is? What type of thing is this?
An equation.
What type of equation? What type of object is this if I were to graph it? I'm just going to keep doing this, and you just shout out the answer when you know what it is. What type of thing is this?
Parabola. Oh, great.
Right? So whenever you have something like for instance, if I had, say, 2x plus, let's go minus 2x minus 3y plus 5 equals 0. I'd say graph that, and you'd go, well, let me get the y by itself. And so we get minus 3y equals minus 2x minus 5. And you go through and you divide through by -3, and that gives you 2/3 x. Uh-oh, did I mess something up? No, that's right, because that one's minus. Okay, good. And then you have minus 5, so plus 5/3. And you'd say that thing right there is a line. And so you haven't known it yet, but you've already been working on this equation. It's just that it's been the special case where the A is 0, the B is 0, the C is 0, and all you have left are the D, the E, the F, and the 0. And like you can see, this is what I did, right? We're used to the way that we've been dealing with this our whole lives, as far as we're concerned, has been you get the y by itself, and you get it basically, you turn this thing into this form right here. Why? Well, because this has a really easy interpretation for graphing, right? Like if I had this and I wanted to draw it, I could say, well, hold up. It goes through here at 5/3. It has a slope of 2/3, and so it looks like this. And I get a nice qualitative graph of this thing. So in other words, let me say this one more time. You're given something like this exists or whatever, and you want to try to you wrap your head around it. In other words, I like to think about it as get my hands on it, right? I want to be able to see what this thing is. And so what do? Well, we get the y by itself, and we get it into a form, right? A general form that we recognize. Okay. And so, all right, there we go. That is the case. That is the first case that you ever learn about this equation. The case is where A and B and C are all equal to 0. And the thing that you have is a line. All right. Can I erase this?
Yeah.
Okay. So questions before we move on to the next case?
No questions.
Okay. Case number 2. This is, I believe, the second case that you learn as you go along doing these. It's the case where B and C are equal to 0. And the thing that you had in that case is some number a, x squared, plus dx plus ey plus f is equal to 0. And then the way that we've learned how to deal with this is basically the exact same thing. We say get the y by itself. If you could isolate that y, then we have a ton of tools at our disposal to go about dealing with that. And so here symbolically, what we would do is say, well, let's get the y by itself. Let's keep him on that side. Get everybody else over on the other side. Minus ax squared minus dx plus f. Divide through by the e. We get minus a over e x squared. Let's write that as a plus negative d over e x and plus f over e. Why do I use pluses? Well, just because. And we say, well, that's just some number. You took some number minus a, divided it by e. You took some number minus d, you divided it by e. You took some number f and you divided it by e. Those are just some numbers. And so in general, we have this type of thing right here. What type of thing is that? The graph, I mean. Okay.
Isn't that a line?
A line has a squared term?
Oh no. That is a parabola.
That's a parabola. Yeah, we've been dealing with these a couple months now, I think. I think that's pretty much all we've done for the last couple months is we've had parabolas, right? Anything with a squared term would be a parabola. We get, in this case, this is another case where we have some general thing, right? Some case of a bigger type of thing. And in general, what we do is given something like this, we say, well, you could get the y by itself. And so we get the y by itself like this. And perhaps that's enough to graph it. That form certainly helps us find zeros and stuff because we have a formula for that. But there's basically with this type of thing, which we call a parabola, there are two equivalent forms that we like. One is like that. The other one is like this. Right there. And we know, because we've done it a bunch of times, we could take something like this, complete the square, right? We factor out the a, you add and subtract half of whatever it is squared, blah, 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 to obtain this type of thing. And so with this, right, there are two general forms of this thing. Given any one of these, right, with any number a, d, e, and f, I could take this, rearrange it to get these numbers here. And if I were so inclined, I could rearrange this again to get this type of thing. And why would we do that? Well, again, this really helps us graph it, right? Like if, for instance, I knew I did all of these calculations, I got this into here, and then I ended up here at the end with, say, a equals, oh, I don't know, -2, x minus 1 squared plus 3. I'd say, oh, I know how to graph that. I could just look at this and tell, right? This is a shift in the right direction. So it takes my cup, shifts it over 1 unit to the right, like that. Then it stretches it by 2 and flips it down. Okay, so it's a stretch and then I flip it down. Finally, I add 3 to it, so it shifts it up by 3 units, and it does something like this, right? So again, let's say this again. I'm gonna say almost exactly the same thing as before. We have a special case of the original type of thing. We have a special case where we take it and get the y by itself and put it in this special form that helps us wrap our heads around it. Why does this form exist? Well, because if you could put that into this form, it's there, all the information is kind of contained there, right? Like this part right here, that minus h, tells me how far to go in this direction. There's my h. This part right here tells me how high up to go right there. There's my k. In other words, like we can't see that if it's like this. That form doesn't really help me out. But if I could rearrange it, do some magic and turn it into something like this, then it helps me not only graph it, but remember, this is how we derived the quadratic formula, right? Dx equals negative b, this bad boy right here, which is really nice because that tells me where these things are. Again, all of this work that we've been doing thus far has been to take this type of thing, rather to take a special case of this thing and get it into a form, change the original way it looks into a way that helps us out. And this way, by help us out, I mean, I could just look at this. I don't need to do any calculations. I don't need to plug 1,000 inputs in and get out 1,000 outputs and plot a bunch of points. I could just look at this and see. Like I didn't do any kind of calculations, but this is a qualitatively accurate graph of what's going on here. And with this information, I could answer a lot of questions now. As a matter of fact, in this way, you could say, what's the maximum of this? Well, whatever that is, that output right there is 3. So I know that the maximum this thing ever gets is 3, etc., and so on and so forth. So again, I'm going to say this one more time because this is so important. We have a special case of one of these things, and we rearrange the way this looks to get it into a form that we like. And in this case, there happen to be 2 forms that we like. But why? Well, because all of the information of what this thing looks like is wrapped up right here. We can, just by glancing at this, and here's an actual example, by glancing at this, we could see generally what this thing looks like. None of that information is right here, right? It's kind of hidden in the numbers. And what you would have to do is, well, get it like that, get the y by itself, find what those numbers are, complete the square, and then finally you end up with something like this. Why do we do that? Well, because now we can wrap our heads around it. It's easy to deal with. You following so far?
Yes.
Okay, so then notice that with these last 2 cases, like everything that you've done in math up until now has kind of had the same game plan. Get the y by itself. And yeah, if you get the y by itself in the first case, then you have the form y equals mx plus b. And we know how to deal with that guy. That's its slope. That's its y-intercept. You could graph it. Get the y by itself. And depending on what you're doing, if you get it like this, easy. That's the shift. That's the shift. That's the stretch. Got it. Now things get hard. And that's why what we're about to do and what, when we start dealing with circles, ellipses, hyperbolas, things are very alien now because the game used to be get the y by itself. Why? Well, because that turns it into a form that we could wrap our heads around. Now, getting the y by itself is no longer an option. We can, and we will later on, we will see a way to do that, but it's actually way more difficult to do that. It's easier, believe it or not, to learn a new way of doing things. And so here we go. Before doing this in generality, we're going to discuss a couple other cases here. There's a special case where the C, the D, and the E are all 0 in the case. So this is going to be the third case we talk about. The C, the D, and the E are all equal to 0. In that case, what we're left with is the AX squared plus BY squared plus F equals 0. And now, now there are a bunch of different cases. Before, with all the other 2 cases that we've done, it didn't matter if, say, the D was negative and the F was positive. We could always just rearrange it so that everything works out. But now those signs do matter. And that is, and this is, well, yeah. And this is what we're going into now. And when we talk about hyperbolas, ellipses, I guess that's pretty much, oh, and circles, right? Those are all kind of special cases of this case right here. Not exactly. We'll get to that in just a second. But this could be a few different things depending on A, B, and F. And so the first, so that's why now it's like, why did we go from parabolas to circles? Well, because believe it or not, or rather, why did we go from lines to parabolas? And then why did we go from parabolas to circles? And why did we go from circles to ellipses? And then we're going to go from ellipses to hyperbolas. Well, because believe it or not, we're kind of systematically going through this equation, trying to wrap our heads around this one equation, but there are a bunch of special cases along the way. And so we start, right, just one more time, we started off by just looking at this, where we have a D, an E, and an F. Then we came along and said, all right, what if you had that, but you added in an A? Then what do? Okay, we have ways of discussing that. Now what we do, and what most books and what I think is a good idea to do, is look at first, what about when we only have an A, a B, and an F? And there are a few cases. The special case of a circle occurs where the A and the B are the same thing. So this is what we're looking at. And there's special case number 1, where the A and the B are equal. And F is a negative number. What do I mean by that? Well, let's just look at what we have. We have AX squared plus, instead of B, they're the same number. Why don't I call it a Y squared? See what I did there? I'm imagining like we had some original equation like 5x squared plus 5y squared minus, say, 10 equals 0. So that's what I'm saying here. We have something like this. F is a negative number, so why don't I write it as minus F, something like this? And then it's like, what do we do with that? In fact, I'm going to rewrite this up here because I want to use that in a minute. So there's that guy. There's a special case of the special case of the special case of the special case of that. Sorry, I had to say that. I'm sorry. Okay, so this is the first type of thing that we learn with these bad boys right here. We say, well, what about this special case right here? What can we do with that? Well, here's something you could do. Like my intuition, given everything that we've done in mathematics up to this point, would be to say, well, get the y by itself, right? That's what we've been doing all along. Let's do that. Let's do that real quick and see what happens when I do that. Get the y by itself. So I'm going to keep the y right here. How about I get rid of that f first? I'm going to bring the f over to the other side by adding f to both sides. I'm I'm going to bring the a squared over. And so I have ay squared equals minus ax squared plus f. Divide through by a, that gives me y squared equals minus x squared plus f over a. Just so you see what I'm doing. So this isn't just purely abstract. Let's do it the same thing with this guy. Let's get the y by itself. I'm going to just take the exact same steps. Let's get that 10 over on the other side. Add 10 to both sides. What I'm doing, right? And you see what I'm doing. This is a special case where I'm using actual numbers. But here, everything I'm about to do is I'm just taking these steps. And so we're saying, I don't care what f is, right? You would do this, then you would take it and you would divide it by a. And that's what I'm going through right now. Just saying, okay, well, let me just take these steps here. We have y squared equals minus 5x squared plus 10. Then I take that thing, divide it through by 5, and I'm left with y squared equals negative x squared plus 10 divided by 5, I guess it's 2. Okay. Okay, so that's all I've done. We're just saying, given any of these numbers, if those first ones are the same and that last guy is negative, you could do this. Okay. Now what? Well, we want to get the y by itself. We have a y squared. How do we undo squared?
Square root.
Take a square root. And when we take a square root, what happens?
Plus or minus.
Yeah, and that's the problem. That's why we're running into a problem here. Everything before, right? When we just had the D, the E, the F, when we got the y by itself, I'm left with one thing. There's no ambiguity. When I had just the A, the D, the E, and the F, again, I could get the y all by himself, and I'm left with one thing. Now, when I go to get the y by himself, we get two possibilities, and that is not helpful for us. That's why things are now so different than what we've been doing all along. Is because we cannot get the y all by himself without splitting this into two possibilities. Remember what this means. This means that y is either equal to the positive square root of negative x squared plus 2, or y is equal to the negative square root of negative x squared plus 2. And the very first thing we ever talked about was functions, right? A function needs to have the property that with one input, it gives you one and only one output. This is something that now you get one input. Uh-oh, there's two possibilities. We're getting two outputs. And it's like, well, why don't we just do that? Well, we will. We'll play with this, and like shortly we'll do something like this. But it's not really helpful if all we're trying to do is graph this thing, or if we want to wrap our heads around it. In fact, going down this route is going to end up being way more work than we need it to be. And so that's why everything up until now, the general form of it, like you're given something, dx plus ey plus f equals 0. What do? Well, you get it into the form y equals mx plus b. Why? Well, because the m means something, the b means something. And I could just look at that and go, oh, that means that we have an intercept here. And that means that the slope of the line is this. Ditto with the parabolas. If I get it into a certain form, I could say, that means it's over here and it goes upwards. This is not as easy as it could be. And that's why we're not going to go down this route. What we do is I'm going to erase all of this because this was just the naive approach. It's like, let's just keep doing what we've been doing. Let's get the y by itself and see what happens. Oh, that's ugly. Can we make our lives easier? Yeah, we actually can. We don't want to go down this route. And so what we're going to do is say, all right, well, instead of going down that road, what do? Well, somebody figured this out. Somebody said, you know what? It would be a lot easier. Check this out. If you do this, get the f on the other side. Equals f. Now I'll divide through by the a's to give you x squared plus y squared equals f over a. And then you take one last step and say, wait a second. If I could write that as something squared, right? So in other words, if I take the square root of it, and then I square it, whatever it happens to be, then I end up with an interesting geometric interpretation. Is that, and this was right when we talked about this, actually, this was the lecture that did not get recorded, but the idea was, well, this thing that you're talking about here can be thought of like this. If this is your X and this is your Y, you're saying, if you're at any value X and any value Y right here, it turns out that this distance, X squared, and this distance right here, if we take Y squared, if you add them together, it equals this squared. And we could realize, well, hold up, that's a circle, right? But that's what we talked about. And I will stop right now and say, did you have any questions about this? Did this thing right here, why this ends up being a circle, did that make sense?
Yes.
Right? And it should, right? And it's kind of intuitive, right? That, yeah, if you could take your wicked looking thing and turn it into this form, in other words, in full generality here, if you could take it and put it into this form right there, then this gives you a lot of information. You could look at that and go, oh, wait, x squared plus y squared, those are like those feet, equals something squared. Well, then that's just the radius of a circle. And so just like before, it's like I could take some weird looking equation like dx plus ey plus f equals 0. And if I could turn it into y equals mx plus b, I can look right away and go, oh, it goes through the x-axis up here at b. And then it has a slope of m, that's a line. Cool, I got it. Same thing here. We could take our weird looking thing, this crazy looking thing, and say, well, hold up. If I could take this and rewrite it like this, then I could see, oh, that thing that you're talking about is a circle at the origin, and it has a radius of r.
Mm-hmm.
Cool. Okay, so that's why we're doing it that way. We could, if we were so inclined, go and solve this thing for y. We could just move this around a little bit, but that's more work than is necessary, actually. It's like, if you're in this scenario, you could just do this, and now you know what that thing is. Cool. Okay, so, all right. Moving along with the, oh, and so let's just kind of finish this up, right? So I can say, what is this thing? And instead of ending up, well, half of the time it's the square root of negative x squared plus 2, and half the time it's the positive square root of blah, 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 blah. We could say, well, hold up, wait a second. Those two things are the same. Let's do this. 5x squared plus 5y squared equals 10. Divide through by 5, that gives me, oh, x squared plus y squared, that's a circle, right? And so 10 is 2. Say, well, what's the radius of that circle? Well, if I can rewrite it in the form that helps me out, I could just say, okay, well, then we'll just do this. Y squared equals something squared. Take a square root of 2. It's a circle at the origin, and it has a radius of square root 2. And now I've graphed that thing, and my life is 10 times easier because I was able to graph the object that has this weird form. So that's the goal. That's the point of all of that. Okay, are we ready to move on to the next special case of the special case?
Yes.
Okay, the next special case of the general thing is where A and B are not equal. If A and B are not equal and F is positive, then what? Well, let's see. A and B aren't equal ax squared plus by squared plus f 0. And this is, I guess, a lot of this is on, oh, and f is still a negative number. And something I haven't said, both a and b are positive. Both a and b are positive numbers. Then the form that we want, because again, like we could just go through and solve it for y, but y is squared, right? So when we get y by itself, we'll be taking a square root, which means we'll have two things that are ugly, like way hard to figure out how something with a square root works, blah, blah, blah. And so luckily for us, somebody already figured out what these things look like. And they've already figured out a really sweet form for us, right? And what to do, the form that we want looks like this. So we get the f on the other side. If we were so inclined, we could declare this is our standard form, and we will keep it like this. And okay, and that's perfectly fine. We could do that. It's just that there's another way that makes things very easy. Just like, now pay attention here, just like we could decide that with a general line where you have some number d times x, some number e times y, and some number f equals 0, and all these other things are gone, we could decide that's how we're going to write our lines from now on. But if you could take that thing and rewrite it in this form right here, then it makes graphing it a million times easier than trying to figure out what the heck that thing is, right? And so that's the game that we're playing right now. It's like, you could go ahead and just deal with that, but it will be easier to get it into a different form. What form is that? Well, we could do this right. In fact, let's just do it. The form happens to be x squared over a squared plus y squared over b squared is equal to 1. And right now, and this is what I anticipate, or what I suspect is one of the big disconnects that's going on, because like you first see this, like, why am I doing this? Why would I take something like this and try to cram it into this form right here? We'll get into that when we stop talking about this big picture stuff. But for right now, let's just kind of complete these pictures that we've been drawing with big picture stuff, for the big picture stuff. So in order to get it like this, what I do is say, well, I need a 1 on the right-hand side. So that in order to do that, I'm going to have to get rid of that f. And so I'll divide everybody through by f. What does that give me? Well, it gives me an a over f x squared plus b over f y squared equals 1. And it's like, well, you're not quite in the form you want yet. It will be nicer. And you're like, why is it nicer? Trust me right now, it will be nicer if we just get those in the denominator. How do we get that in the denominator? We talked about this last time. You divide by the reciprocal. Okay, so I'm just going to do that on faith, and then we'll come back and check it. I'm going to say, okay, divide by the reciprocal of those things. Get this out of the way here. What I'm looking for, this is my goal. If I could turn it into this, then this equation right here, that bad boy, has all the information I need in order to graph that guy. Okay, so saying I'm not quite there yet, but if I could turn it into blah, 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 the same way as we were doing with trying to get this guy into y equals mx plus b, it's like, well, if I could turn this into that, so I'm just going to keep plugging along and let's see what we could do. I'm gonna go on faith here, Justin. You tell me I could just divide by the reciprocal and we'll see. I'll just do it on faith and then I'm gonna come back and check it. It says go F over B right there. Can you read that? I'm really making this small, but that should be an F over A in the denominator. And I'll just make it look better. Not bad. F over B in the denominator. Let's just check. Let's just come back and check. Over here, I had A divided by F, which I said was the same thing as multiplying by A over F. Then I said that's the same thing as having an F over A in the denominator. Whoa, 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 whoa. Well, let's go backwards. Let's see. And I'm just going to do this with one of them. And if it works with one of them, it should work with both of them. So I'm just going to take X squared over F over A. And I'm going to say that's the same thing as taking whatever is in the numerator and multiplying by the reciprocal of that thing. So that's the same thing as multiplying by A over F. Do you believe that?
Yes.
So then I'm going to say, okay, well, that's the same thing. Since I can do multiplication in any order, that's the same thing as having A x squared and then just dividing it by F. Yeah, I don't see why not, right? You have a numerator and a numerator, something in the denominator, whatever's in the denominator just stays there. And then I could see like, yeah, that right there is the same thing as that right there. And so, okay, I did some jumbling around and some crazy stuff, but it means the exact same thing. Why would I do that? Well, because ultimately, and we'll see this in a minute when we start to do this, this way is kind of, it's like the analog for the y equals mx plus b. I'll be able to just look at this thing and go, oh, that's where that goes through this axis. That's where that goes through an axis. And so you got to kind of take it on faith right now that we're heading in the right direction, that whoever came up with the idea, hey, dude, if you have like this type of thing with these, like you could just write it like this and it'll make your life easier. And you go, okay, but we'll come to believe that in a minute. So I'm on the way, right? We're almost there. And this, now that we're in this situation here, we have two numbers in the denominator. And what we're doing is kind of like earlier when we had x squared plus y squared equals 2. It's like, if I could take this thing and write it as something squared, then I know that whatever number that is the radius, right? And so why would I do that? Well, to make my life easier, rather than looking at that and going, what's the radius of that? And then having to go, well, the square root, the square root of 2. I could just say, well, you know what? Why don't I just go ahead and do that? And now it's obvious. What's the radius of that guy? Well, whatever's in there, square root of 2. And so that's kind of the step we're going to take right now. We're going to say, you could say, okay, what is the A value? Well, well, that's not squared. I guess I would have to take a square root and then square it. So let's just do that. Let's just take that extra step and write it in the form that helps us out. In other words, whatever number ended up down there, we'll just take the square root of it, f over a, and then square it. We'll take the square root of f over b, whatever that happens to be, and then we'll square it. And now our equation is in the form that we want, that will help us out. In the same way, earlier, when we had a circle, and it's like, well, it would be easier to write this like this. That way, all I have to do is look at it and go, that's the radius. Don't have to use my brain. And so, and that's again, like, you know, if we had dx plus ey plus f equals 0, we could leave it like that. Or we could do our manipulation and get it so that the m is by itself and the b is by itself. So I could go, it goes through the y-axis at b and it has a slope of, say, 5. And so, again, all of this is just to make our lives easier. And it turns out that this way is way easy to, if you could take your thing that's like this and turn it into this thing, it makes graphing it very, very simple. Okay, so there's a couple more cases, and we're oh, can I erase this stuff? Are you tracking so far? Are there any questions?
I'm tracking.
Okay, so okay, there are a couple other special cases. I don't want to do it. We'll come back and do hyperbolas in a minute, but when we go to talk about hyperbolas. But right now, we're only going to talk about one more special case of this equation. And it's going to be this. It's where C equals 0. And so the thing that you end up with looks like this. Well, if C is equal to 0, you have this plus dx plus ey plus f equals 0 right here. And we're going to stick with the same restrictions here. The special case of the special case is where A is not equal to B, where A and B are both positive numbers, and F is actually, it doesn't, we don't really know yet. Actually, is it less than 0? It may or may not matter. We're not, it's not necessary in this special case that F is necessarily negative. You'll see that in just a second. Why? Well, what do? Well, earlier, someone figured out that if you could turn your old case into this, that makes your life way easier. And it turns out that, like we were saying before, like the same way with parabolas, that you could write your parabola like this, x squared plus bx plus c. You could write it like this, like that. And we went over how adding or subtracting to the input of a function moves it left or right. And here's another thing to notice. We said that this thing also, we could write it this way. We could also write it like this: y minus k equals ax minus 8 squared. And it turns out then if you do it that way, right? Remember, adding to the output of a parabola shifted it up. But if you're doing it on the inside of parentheses like this, it has the opposite effect, right? Like subtracting a positive number from x moved it to the right, it moved it in the opposite of the positive. Subtracting a positive number from y will also move it in the opposite direction, moves it towards the positive. And so this is, we're going to use this principle here, this idea to say, well, wait a second. Since we know what this thing does, like we know that this, which we will in a second, right, that this thing is centered at the origin, in the same way that the x squared plus the y squared equals, r squared was a circle centered at the origin. And then we talked about, well, you could take this circle and shift it in different directions. This would just be the circle shifted by, it would be the same circle, but shifted right 1 unit and down 2 units. The same principle applies here. It's just that, okay, we have a little bit different because you have something in the denominator, but we could say the same thing's going to be true. this thing would be an ellipse centered at the origin. And so if you took it and shifted it like this, well, we could draw that pretty easily because we just imagine an ellipse that's centered. We imagine this, our original ellipse, what that would look like. And then we say, well, if you just took that original ellipse, this says to shift it 1 unit to the right, and the y plus 2, I just changed that to a plus 2 to kind of match with that, would shift it 2 units down. And so, since we know things about shifting things that are centered at the origin, we could say, well, hold up. We could take this general looking equation. I just went ahead and erased that. I hope you weren't copying that. Or I hope you weren't in the process of copying that down. Good. Good. Okay. So what we do is say, well, hold up. We could do a similar thing here. We could take this thing, ax squared plus by squared plus dx plus ey plus f equals 0 and say, you know what? I know how to complete a square. And if I just rearrange these guys, ax squared plus dx plus by squared plus ey, and I'm going to go ahead and bring my f to one side for a second. And then I just go through and complete the square. And I'm not going to do this in full generality, but this is what I would start to do. I would say, well, divide the a out and then add half of it squared, d over 2a squared minus d over 2a quantity squared, and so on and so forth, plus factor this guy by squared plus e over by plus etc. squared minus whatever squared equals f. And at this point, you're like, why would you do that? It's the most horrible thing. We never want to complete squares. It's terrible. You say, well, hold up, because watch what's going to happen. We'll have an a times something squared. Why don't we call it a times x minus h squared minus some number, we'll call it n, plus b times y minus some number, let's call it k squared, minus some number, we'll call it m, equals f. And we move along, right? And we get, okay, well, then that gives us a x minus h squared minus an plus b y minus k quantity squared minus bm equals f. And then we just move these guys over to here. We need a new name for that number because I'm not about to just keep writing f plus an plus bm. Why don't we just call that whole thing g? So a new number over here. We're going to call it g, right? You see what I'm doing? I'm taking the an over to the other side. I'm taking the bm over to the other side. And then we're going to have f plus some number plus some other number, and all together that number, why don't we give it a new name? We're just going to call it g. It's left on the left hand side. Well, a x minus h squared plus b y minus k squared is that guy. Didn't matter what numbers I started off with. You could always do this. You could always do this. And if a and b aren't equal, and if a and b are positive, then you have a positive something squared plus a positive something squared equals some number. And this is where the question was. It's like, well, maybe you did some stuff. If that's negative, well, it depends. You're about to add a whole lot of other numbers onto here. So basically what it comes down to is if in the end you end up with a positive number over here, and you're good to go because you could just divide everybody through by g. to get a 1 on this side. And you get a over g x minus h squared plus b over g y minus k squared. And we're not going to go through like we did last time. I think you know what's going to happen. We take the reciprocal of that, put it down into the denominator. Then we take the square root and square it. Why? Well, because it'll turn it into this nifty form that we want. We'll be able to rewrite this thing as x minus h quantity squared over some number, call it a squared, plus y minus k quantity squared over some number, call it b squared equals 1. And lo and behold, we could say, well, wait a second. You took this special case, you could rearrange it to put it into a form that we could actually deal with. Like we could actually wrap our heads around this. We could say, well, this is a lot like the x squared over a squared plus y squared over b squared equals 1, which we know how to graph. And then we say, well, you've just shifted it over by h and you've shifted it over by k. And so we can actually graph this guy, and all of the information for it shows up right here. Just like earlier, when we were thinking about, we have some general, let me know when you got this. I'd like to get rid of this stuff.
Okay.
And you see what I'm doing, right? Like this, does this look like just completely, like you could imagine if this were a 2 and that were a 4, I would have pulled the 2 out and I'd have 4 over 2, and you know how to complete a square. And so that's basically all I'm showing right here is like, yeah, you'd have some numbers that would pop out. You'd end up with plus something squared minus something squared, blah, blah, blah. And you'd finally reduce it down to this right here. Does that make sense?
Mm-hmm.
Okay, so that's all I'm saying with all that. It's like that doesn't matter what numbers you started off with, you'd be able to go through and do the calculations until eventually you would be left with this right here. And so, okay, in the same way that having your parabola, which you, well, let's do it, just do it like this. You started off with some crazy parabola, ax squared plus dx plus ey plus f equals 0. And you said, you know what, I could do some rearranging and I could do some calculations to find that this is the case. So why? Well, because now all the information's right there. I could see that this parabola is just the original cup shifted over by h, stretched up by a, and then shifted by k. The same thing is true here. We did all of this work to take this ugly looking thing, moved it around. Why? Because now I could see, this, and we'll go, this is the whole point of, or what we're doing with ellipses and what we're about to go into. We'll be able to see, oh, this is just the ellipse that's stretched out to a and minus a. It's stretched up to b and minus b, and then it's been shifted over h units and then over k units. That's why we're doing this. That's why this thing exists and what we're doing, because writing it in this form makes it super easy to graph. Writing this in this form makes this super easy to graph. Writing this into this form makes it super easy to graph. This is the same game we've been playing pretty much the whole time since you've been in algebra. It's just now all of these forms look a little bit different. And now we're taking a huge step because it used to be, boy, that's loud. I'm sorry. Oh, terrible twos.
Yeah, I know.
Yeah. Yeah. Okay. So actually not bad. Like this is about as bad as it gets right there. It's, you know, a good 2 minutes of just and then. Okay. So, all right. Finally. Why is that form so useful? So we did this one yesterday. This is one of the special cases. This is the special case. Actually, if we were to write it all out, right, this would have been with the bx squared, ax squared plus by squared minus f equals 0, where the a is 9, the b is 16, so they're different. They're not the same number. And then the f is a negative number so that we could bring it over, stuff like that. Now, pretty much with any of these, what we could do, one way of dealing with this. You want some more orange, buddy? Okay. Here you go. Okay. So bear with me for just a second. Again, we could do something like this. Let's go 4x minus 2y. Let's go equals. Let's go equals 6. Now, put this in the form y equals mx plus b and tell me what you get.
Y equals 2x minus 3.
That?
Yeah.
Okay. So on one hand, we could take this thing, turn it into that. That way we could graph it and say, okay, it goes through at minus 3. And it has a slope of 2. So it goes up like that. That's one way we could graph it. Another way we could graph it is to find where it crosses, knowing that it's a line. We could say, well, if I find where it crosses the x-intercept and what the x-intercept is and what the y-intercept is, I could find that. And so in general, now, I mean, with anything, how do we find the x-intercept?
The x-intercept?
How do we find an x-intercept of anything? Not just a line, but of anything.
Set y equal to 0.
We set y equal to 0. So define the x-intercept. We set y equal to 0. So let's do that and see what we get. So equals 6. Yeah. I'm not even going to bother to write 2 times 0, right?
Yeah.
I'm just going to say, pretend it's not there. Right? I know what a 0 in there for y is going to do. It's just going to give me that right there. So I'm going to just do that. And then what do? I guess pretty easy to see what we do. Getting the x by itself, we just divide this by 4 and we get that x equals 6/4, which I think is 3/2. Okay, so there's 3/2 right there. Now, what's the y-intercept?
Set x equal to 0.
There we go. We set x equal to 0. So let's do that in the original equation over here. I don't know about you, but I get y equals -3. Why? Because I didn't even bother to write that part down. I know I'm plugging in a 0 for x, so he doesn't even show up there. And so this entire equation reduces down to -2y equals 6. That's pretty simple. I'll just divide both sides by -2. Gives me a -3 right there. I have my 2 bits. I have 2 points. I could draw a line, right? I could say, okay, let's just draw it. In fact, let's do it right. No, it's terrible. X equals 3/2, just like that. Peter, get down. Get down, get down. You cannot climb up here. You want some orange? Okay, here. Here you go. Yeah, and you could have the peel too. Yeah, the peel. So sorry. So I say, okay, the X goes through here at 3/2. The Y goes through here at -3. And so I know it's a line, and so it goes right through here. Okay, two ways of doing this, right? If we were trying to find all the points, maybe we'd save ourselves a second by doing it this way. But again, we could, having it this way, find out what that point is too. It's not, we're kind of missing the forest for the trees there, because both of these with a line, it's super easy to do either way. And so, okay, there's two different ways of doing this. One form, though, just looking at this guy right here, the original way, I don't have any information as to the shape of this line. I mean, at least not right away, unless I do some calculations in my head. This thing doesn't really give me any information about what this line looks like. Whereas this one, I don't even need to graph it. I basically can see what it's an upward line, right? It's an upward slope. It's going up by 2 for every run of 1. I go up 2, so it goes up. And it's also been shifted down 3 units. So it goes down here through 3. There's a lot of information contained in this right here. So let's do both methods of figuring this guy out. First, let's just do the intercepts. And so actually, I really have to use the bathroom. What I would like for you to do while I'm doing that, if you can, using the method that we did before, find the X-intercept and Y-intercept just by plugging in the appropriate values here and then solving for X and Y. And I will come back when I'm back from the bathroom. I will also do it, and we will confer on our results. Sound good?
Sounds good.
Okay. Okay. Are you close?
I'm finished.
Say what?
Write it down. I'm finished.
Okay, cool. So what'd you get?
That.
Y is plus and minus 3. X is plus and minus 4. And just, I want to talk through this. So setting X equal to 0 gives me 16y squared equals 144. So I take 144 and divide it by 16. That gives me, I reduce that down to 9. 9's a perfect square, which is cool. Take the square root, gives me both a positive and a negative answer. Gives me positive and negative 3. So I know that the Y-intercepts are up here at +3 and down here at -3. Okay, now ditto over here. Plug in a 0 for Y. That gives me that equation. And so I say, okay, I divide through, because I'm trying to get X by itself. Divide through, I get 144 over 9. Which reduces down to 16. The square root of 16 is plus and minus 4. And so then that means this goes through here at +4 and -4. Okay, so I found the X and Y intercepts by doing it that way. And one thing that I gloss over this, the book glosses over it, everybody's going to gloss over why the shape of this thing is the way it is. Like, how do we know that it doesn't come down like this and look like some kind of star thing or whatever? Why is it that it bends out like a stretched out circle? Well, we could go into that and see in the same way before, like when we were dealing with parabolas, and we took and multiplied a parabola by something, it stretched it in a certain direction. We could go through systematically and show why this is indeed a circle that has just been stretched in one direction and stretched in another direction. But we're going to just kind of right now, I guess, take it on faith that that's what's going on. I guess really just in the interest of time, that's what this is. This thing is a circle that has been stretched by a factor of 4, or rather, has been stretched, yeah, I guess by a factor of 4 in the x direction, and been stretched in the factor of 3 in the y direction, and that's what we end up with there. Now, that's one way of doing it if you have something like this. It's by no means, at least to me, it's by no means obvious that I look at that thing and say, oh yeah, plus and minus 4 and plus and minus 3. But if we turn this thing into the form x squared over a squared plus y squared over b squared equals 1, it will be very apparent that that's the way that it is. So let's do that. Okay, let's start with this thing right here. And like I said before, the first step we're going to take is to get this thing to be equal to 1. And so I'm going to have 9x squared plus 16y squared equals 144. And I'm going to take, again, my first step is like, I want to turn this thing into this kind of thing. And I don't have a 1 there. The only way to get a 1 out of that, and I don't mean like, you might say you could subtract 143 from it and get 1. It's like, yeah, but I'd have to do that to the other side. And then my other side won't look at all like what I want it to look like. So the only way to go forward, keeping in mind that I want to end up looking like this, to get a 1 is I have to divide by 144. So I'm going to do that to everybody. I'm going to do that here. I'm going to do it here. And I'm going to do it here. Now at this point, what I could do, there's a bunch of ways I could do this. I could think about this. In fact, I'm going to do this 2 different ways with the first one and with the second one. With this x squared and the 9 and the 144, I could just straight up reduce that guy and say, okay, 9 over 144. And the way I like to do it is to say that's the same thing as 3 times 3 over 12 times 12. And 12 is 4 times 3. So that'll cancel one of the 3's, leaving a 4. That'll cancel one of the 3's, leaving a 4, leaving me 1 over 4 times 4, which is 1 over 16. You could also, if your brain's good enough, go 144 divided by 9 is 16. So the 16 stays in the bottom. I can't do that. That's too, I can't, I barely know my sixes, my multiplication tables. So, you know, trying to figure out 144 divided by 9, that's way above me. So that's how I like to do it. But anyway, now another way we could do this. Notice when, like earlier, when we were playing with this type of thing, and I had a B and I divided it by an F, I said, we could rewrite that like this. Over F over the B. And it's, I'm not, and by the way, what I'm doing right now, I'm not suggesting that you should do it this way. I just want to make you aware of something. Like, so right now I could say 16y squared over 144 is the same thing as y squared over 144 over 16. Right, and isn't that basically what I did right there? Right, when I reduced the 9 over 144, I said, well, 16 ends up there. Well, yeah, that's because 144 divided by 9 is equal to 16. In other words, that's what I have in the denominator right there. I took one of them and just kind of flipped it. Then I just went and reduced it, right? In this case, the 16 comes downstairs and the 144 stays right there. And in this case, yes, 144 divided by 16 is 9, which is cool. So let's go ahead and rewrite that. Y squared over 9. Are you caught up? Are you up to this point?
Yes.
Okay, so now my form says, well, if you could rewrite this thing as some number squared, then your life will be easier. And you go, okay, I guess. And it says, if you could rewrite this as some number squared, then your life will be easier. I'm going to be really explicit here at this step and say, well, let's say I don't know what the square root of 16 is. I could just write the square root of 16 squared. Right? Or if it weren't a nice perfect square, if it were x squared over 7, it'd be like, and then I would just say, well, you know what? Just how about square root of 7? So same thing here. Square root of 9, just like that. That's what I'm doing. And you'll notice, right? Like everything I've done here, these are the same steps that I took. And I'm going to end up with pretty much the same information, but now the information is going to be organized in a way that helps me out. And I could say, this is the same thing as 4 squared, y squared. This is the same thing as 3 squared. And now I have it in the form that I want. And what's really cool here, and so why does this form exist? Well, because if you had something like this and you simply just went and found the zeros, you would go through all of these calculations and you would find that y equals plus or minus 3. You would go through all these calculations right here, right here, right here, and you would find that x is equal to plus or minus 4. And so it's like, well, we could do that all in one fell swoop if we just rewrite this equation in this form. And it's exactly equivalent. We end up doing the exact same operations both ways, no matter how you want to do it. So it's like, well, rather than having this thing, which I can't look at that and have that just make sense to me. I can't tell you where that thing goes through and looks like what. So why don't I just first, the very first thing I do, rewrite this in this form. And so we go through and blah, 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 blah. And now that it's in this form, I really don't need to use my brain. I know that by putting it in this form, the reason this form exists is so that I could just look at it and go, yeah, it goes through the x-axis here at plus 4 and minus 4. It goes through the y-axis here at plus 3 and minus 3. All the information is right there. Now, the same way as when we take our parabola and turn it into a x minus h squared plus k, I could just look at it and go, okay, it's been moved over here and moved up there. Boom, all the information is right there on the page. That is the utility of this equation right here, is that this does not tell me any information. I can't see what that thing looks like. But when I look at that, I could tell you exactly what that thing looks like. It's a ellipse, or rather, we could think about it. It's a circle, which has been stretched by a factor of 4 in the x direction, and it's been stretched by a factor of 3 in the y direction. And so that's why this form exists. That's why we spend so much time saying, turn this type of thing into this type of thing and then graph it. Okay, any questions?
No.
Does this make sense?
Yes.
Do you believe that these two ways of doing it are indeed equivalent?
Yes.
Yeah, they are, and it's, and so in the same way, right, like we could, if we wanted to, write every one of our lines in the form we could write it in the form dx plus ey plus f equals 0, but I can't just look at it and gain information. Same thing here. We could decide we will write all of our ellipses like this in this form. Okay, but if you change it into this form, then all you got to do is say, yep, okay, over to 4 and negative 4, 3 and negative 3, way easier. So that's the utility. That's what that's all about. Okay, do you have any specific questions about homework and stuff like, or about like what wasn't making sense? Have I cleared anything up with this talk so far?
Oh, this top, yes, this is fine. Yeah, this makes sense.
Okay, cool. So then in that case, what I would like to do is do a few examples and we will revisit this order of doing things here because
I was gonna say that I understand.
Mhm.
I start not understanding when we start moving it.
Okay.
That's the only part that trips me up.
Okay, then that's why I wanted to present a new way of doing this stuff.
Okay.
So, okay. Let's do this one. This is number 12 from the chapter 10, section 3. And what we're going to do is we're just going to graph. That's all we care about. We're going to graph this guy right here. It's already in the form that we want. And it is, well, it's almost in the form that we want. Okay, so first off, there's one big glaring difference with those denominators. And if you like, you could keep it like this, but I think it's way easier to write those denominators as something squared. How can we rewrite this guy?
Hold on.
Okay.
So that could be x minus 2 squared over 5 squared.
5 squared, there we go. I took the square root of 25, you get 5, and then I just square it, and I end up right where I started. What about 16?
4 squared.
4 squared, which again is not strictly necessary, but it's nice because now I could see something really easy. And what we're going to do now is very much like when we had something of this form right here. If we had, say, 2x minus 2 squared minus 3. Let's say we had that. Okay, what would I do? I would say, well, this is a parabola, right? This is as though we're taking the parabola x squared. We know what x squared looks like. And then we do it in the order as we move out, which is not, this is where this is a little bit different because now we have 2 inputs. We don't have an input-output relationship anymore, so things are going to get a little weird. But let's just go through this reasoning real quick, and then we'll see how this relates to what the new way of doing things. So we say, well, this thing is a parabola. It is very much like x squared. It's just as though you took x squared and you first shifted it to the right 2 units. And so, okay, we take our original parabola, shift it to the right 2 units. And remember how we did this? We imagine that we really care about the vertex. We're going to take that vertex and shift him over here 2 units. So that this thing is x minus 2 quantity squared. Then we took it and it looks like we multiply it by 2. So that has the effect of stretching it up, but it's not going to change this bit. And so, okay, cool. So we stretch him up like this. And now this last one that I drew is 2 times x minus 2 squared minus 3. Then, not minus 3, we haven't done that yet. Okay, so again, we look at this thing and we say, all right, it's like you're doing this first. You shift them over to the right to get this guy. And that's the graph of just plain old x minus 2 quantity squared. Then we take it and multiply it by 2. So that stretches everybody up. All of these points get pushed upward. Then we said it's like you're taking your output value y, the y values, and subtracting 3 from them. So this brings the entire thing down by 3 units like this. And so we're still here at 2. We've gone down to -3 like that. Peter, no, you can't be up here, buddy. You're gonna get hurt. You're gonna get hurt. You want some orange? Here. There you go. So, okay. We're gonna use a similar kind of reasoning with this here. We're gonna say, all right, you know what? I don't know what to do with this and this. But you know what I do know is if, and again, right, it's like looking at this, I don't know what to do with that, but I know what to do with x squared. X squared is the easy thing to deal with. I could draw it. I know where it lives. I know what it looks like. And then we take the easy thing that we know about, and then we do our shifting and blah, 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 blah. Same kind of thing here, only instead of starting with just x squared, we're going to say, well, you know, we could cut to the chase here and say that this thing is very similar to this thing where we haven't done any shifts. And so we're going to imagine first that we're just graphing this guy right here. If that's the case, what are the x-intercepts and what are the y-intercepts? We shouldn't need to use our brain for this.
+5 and -5 and +4 and -4.
There we go. The x goes to -5 and +5, and then it goes to positive. The y goes to +4 and -4. Really don't need to use our brains. That's the beauty of having it in this form. If you want, we could go and plug in zeros and all that stuff, but it's already in the form that we want, that we know is going to work out. So I could draw this thing. Okay. And now all of these things, the only thing that we're doing now is just kind of like before. We had a shift with our parabola. We had a shift to the left or to the right, and we did that first. And then we did our upwards and our downward shift, and we did that second. Let's do it in the same order here. We could say, okay, then we're going to just step by step get this thing that we can wrap our heads around, right? I could wrap my head around this. I could draw this. I could get a feel for it. Now, how could I take the thing that I can draw, the thing that I know about, and turn it into this thing? We'll do it one step at a time. We'll do our x shift first. So just like with the parabola, the x -2 shifts this thing in which direction?
It goes right by 2 units.
It goes right by 2 units. And so now we got to use our imagination. And we imagine, okay, if we started with this guy, we took that, and you know, like when we were doing it with a parabola, there's only one point of interest really, and it's that it was that vertex. And we took the vertex and we pulled him over 2 units. In this case, there are 4 points of interest. And that's what's kind of a pain about all of this stuff. But we could just imagine, okay, that +4 and -4 that lives there on the y-axis, we're just taking those, 2 points and pulling them 2 units to the right So now here where X is 2, we're up here at +4 and -4. So those are those guys. Now, the +5 and the -5, they've also been shifted to the right 2 units. So where does the +5 end up?
Okay, so they all get 5.
Yucky.
The positive side.
Yeah. So let's take this +5 that's here on the x-axis, and we're going to shift him 2 units to the right. He ends up where?
7.
7. And then the other one ended up where?
-3.
-3. There we go. -3. And so this is just kind of helping me to draw this figure here. Now that I have these 4 points, now I can say, okay, then that's the same thing as that. It's just been shifted. We took our original one that we can wrap our heads around. And we didn't start like, it's funny because with a parabola, we start with x squared. We start with about as bare bones as you could get. And then we shift it, then we stretch it, then we shift it again. In this case, we don't have to start with like a circle and then do the stretching and then do the stretching and then do the shifting. We could just say, well, I could wrap my head around x squared over 5 squared plus y squared over 4 squared equals 1, because that's a pretty easy thing to draw because it's in that form that we want. And so now I can say, okay, well, then we'll just step by step get it closer to doing this. And so we shift, this says to the right 2 units, and we get this picture here. Now let's do the next shift. Y +3 shifts in what direction, how many units?
Down 3 units.
Yes, down 3 units, which sounds weird because up until this point, we said you're adding to y. Yeah, that's when y is an output. We do not have a function. And so, what do you say? Yes, here you go. And so, yes, this shifts this whole picture down 3 units. So let's draw that. So let me do this here. There's x, there's y. Okay. So we're up 4. So what I'm going to do, I'm going to start with the up and down axis first, called the minor axis, because it's the shorter one, right? The up and down one from 4 to -4 is smaller than the gap from 5 to -5. So we call that the minor axis. I'm going to start with that guy and just imagine that I take this picture here. I shift him down 3 units. That takes the top point, which was at 4, and brings it down. Peter, it's all gone. It's all gone, buddy. Sorry. Where does it take the bottom point? That bottom point ends up where?
2 -7.
Yep, -7 is that lowest point right there. Okay, now the points that were on the x-axis, they're not moving right or left anymore with this shift. And actually, let me go ahead and write down the function, or write down the object that we're graphing right now. plus 3 squared over 4 squared equals 1. Okay. So we just shifted everything down. So the thing that was at -3 is still at -3, but he's just been brought down to where?
-3.
-3. So he should be at -3 -3. So I'm going to put that right there and label it like that. Okay, ditto with the 7. The 7, he's still not moving left or right. He's still up at +7, but he's been brought down to what?
-3.
-3. Okay. Now here's one of the hard parts, and we did not discuss this last time. So first, so check this out. So this part's pretty easy. There's only one way it could look. Look something like this. This comes back up this way. Sorry, that's really ugly. Now here's the question. Does this thing go through up here and down like this? Does it go through here down like that? Does it go through down like this and then end up over there? Because I know I'm really terrible at drawing and I may not have drawn these right. And even if I do, like, good, does it really come up and then down that fast? I don't know. So what I suggest to do is to just take a guess. And if you're wrong, we'll figure that out along the way. My guess, just by the way I've drawn this, which is probably messed up, my guess is that it comes through the y-axis, then goes through the negative x-axis, and then comes down to -3. But remember, I might be wrong about that. But this is my guess. This is what I think this thing looks like. What's going to tell me if I'm right or wrong, though, is when I go to find the actual intercepts, because we have an intercept here, an intercept here, intercept here, and an intercept there. And what I'll figure out is when I go to find my y-intercepts, if one of them's positive, then I got the right picture here, right? However, if one of them is negative or 0, then I'll need to redraw my picture. Does that make sense?
Yeah.
What's happening here? Yeah. And so at this point, just take an educated guess, or not even educated, just take a wild guess. And I was like, and if you've messed it up, which is possible you may have, then you'll be able to correct it when you go to find your actual intercepts. Okay. So now you'll notice I'm not doing this right now. I'm doing this completely differently, right? And the method I'm using right now will lend itself to a different set of instructions. And so we'll go over that in a second. I'd like for you to try those and see if maybe it will maybe that way will be better. But are you following so far? Given something in this form, we can start by saying, okay, pretend there's no right or left shifts and just draw that guy. And then say, okay, well then to get to this point, all we need to do is a shift and another shift. And so we do those shifts. Does that make sense thus far? And every time you're doing those shifts, you're just taking all 4 of those points and just imagining, okay, it's coming up and we could find where they are. That's cool. And if this way of doing it, if you like doing it this way, or if this way just makes sense and feels crisp and it's good, plug along with it and forget everything we talked about before that other way of doing it. And what I'll do is I'll boil this down with some steps here in the end, and it might be more conducive to everything. The way that I laid it out last time is like conducive to only have to drawing things once. Like, so in other words, it's the laziest way you could do it was the way that I was doing it, but it's conceptually just, I could see it's kind of a nightmare. So forgive me. So, okay, now we're almost done with this graph. The only thing we need to do is find the intercepts. Tell me how to do that. Let's find the X-Intercepts. What do I do with my original thing to find the X-Intercepts?
Set y equal to 0.
Set y equal to 0. So let's do that together, or rather you do that and I'll do it and we'll confer at the end and see if we get the same thing. So setting y equal to 0, that gives me, starting at the top, we have x minus 2 squared over 5 squared plus, I'm plugging in a 0 for the y, which just gives me 3 squared over 4 squared equals 1. So that's where we're starting. The goal is to get the x by himself. So the last thing that happens is plus this. So I'm going to subtract that from both sides, giving me x minus 2 squared over 5 squared equals 1 minus 3 squared over 4 squared. I suggest keeping the denominator in terms of 4 squared and not writing it as 9 over 16. You can if you want. That's if what I'm about to do is really tricky, you don't have to do it this way, but you'll see why I do in just a minute. So what I'm going to do is say, okay, it'd be nice if I could get a common denominator here. And so all I'm doing is saying that 1, and you'll notice that since this is a hyperbola or an ellipse, it's always going to be equal to 1. And so the step I'm about to do will always be what you do. I'm just going to rewrite 1 as 4 squared over 4 squared. If you don't like that, we could have said, well, that's 1 minus 9/16, which is 16 over 16 minus 9/16, which is 7/16. I prefer to keep it with something squared in the denominator. And so we have a common denominator of 4 squared. 4 squared is 16, minus 3 squared is 9, and that's where that comes from.
Okay.
And so, okay, moving on, that gives me x minus 2 squared over 5 squared is equal to 7 over 4 squared. Or you can write it as 7 over 16. That's cool. And so we're almost there. We're going to multiply both sides by 5 squared. That gives me x minus 2 quantity squared is equal to 5 squared times 7 over 4 squared. And this is the payoff for doing it as 4 squared, is that now when I take a square root, I really don't have to use my brain. That 5 squared over 4 squared is going to come out as 5 over 4, which is really cool. And so I'm going to give myself a little bit of room here. So I take square root, I get x minus 2 equals plus or minus square root of all that stuff. 5 squared times 7 over 4 squared. The 5 squared comes out as a 5. The 4 squared comes out as a 4. Now, had you done it with a 16, you would have the square root of 5 squared times 7 over 16, and you'd end up with the same thing. You'd say, oh, wait, I could pull out a 5 from there. Oh, it's over 16. I could pull out a 4. So you'd end up with 5 quarters times the square root of 7. But however you want to do it, it's all equivalent. I prefer to just keep it in squared terms because it's easy to see what we're doing. We get x minus 2 is equal to plus or minus 5 quarters times root 7. This used to really bother me to write it as times root 7. It might look nicer if you do it like this, because that's kind of, but you can see that's the same thing as that. And if I wanted to, I could write that as 5 quarters times the square root of 7. Those all mean the same thing. this way looks a little nicer because you can imagine that what you've done here is you've gone into here, 5 squared times 7 over the square root of 4 squared. And so then you say, oh, that's 5 times the square root of 7 all over. Well, that's just a 4. And so doesn't matter how you write it, they both mean exactly the same thing. Okay, now finally, we get that x is equal to, adding the 2 to both sides gives us 2 plus or minus 5 root 7 over 4. And so, yep, indeed, this thing says that the X-intercepts occur at 2 plus a given distance and 2 minus a given distance. And I could go ahead and label those right here. And this is where we're going to find whether or not we did our picture right. With this first set of intercepts that I get, I'm gonna check now whether or not this number 2 minus that amount is indeed less than 0, or if I screwed up my picture. Because if I find that 2 minus that amount is bigger than 0, if it's a positive number, well, then I'm going to need to redraw my picture. I'm pretty confident this is correct. Can I get rid of this work that we've done right here?
Yes.
Okay, so you feel comfortable with finding those X-intercepts right there?
Yes.
Okay, it's tricky. It's very tricky. It's very tricky. But this is actually, you've been doing this for some time, right? Like with parabolas and stuff like that. It's just the context is a little bit different. And now the equation isn't exactly in the form that you've been used to. And now we have a bunch of squareds everywhere. But ultimately, it's the same game. So what I'm going to do, I want to know, this is what I'm asking myself. Is it the case that 2 minus 5 times square root 7 over 4? I'm asking myself, did I draw my picture the right way? So I'm asking myself, is that number indeed less than 0? You could plug this into a calculator. I hate calculators and I want to forbid their use forevermore, but you could use a calculator. But here's the thing. I think this is easier than getting out a calculator personally. We're just trying to figure out, is that true? I have 2 minus something. Let's add that something to both sides. In other words, is 2 less than 5 root 7 over 4? That's what I'm asking myself. How about we multiply both sides by 4? Because I still don't know if 2 is less than that number. I have no intuition on how big that number is. 5 times the square root of 7 over 4. No clue. Like, really, honestly, I'm not just saying that. I have no clue how big or small that number is. So let's multiply both sides by 4. In other words, what I'm doing here, right? I'm trying to turn this, as of right now, I have no intuition for that. I have no intuition for this. So I'm just going to manipulate this thing until I get something that I do have an intuition for. Is 8 less than 5 times the square root of 7? Again, I don't know. I have no intuition of what this is. But if I get rid of that square root, I may have a better idea. So how do I get rid of a square root? Well, I'm going to have to square both sides of this thing. Square both sides. So I'm going to square both sides. Squaring 8 gives me 64. And we're asking, is that thing indeed less than that? Well, 5 times root 7 times 5 root 7 is 5 times 5 is 25 times root 7 is just 7. Or in other words, square that and square that. 25 times 7. And is 25 times 7 bigger than 64? I think so. 25 times 4 is 100. So yes, that's big. So now Okay, you see what I've done here? I've asked myself a question and I have no idea whether or not this is true. And so I'm just going to manipulate it until I could finally get something that, oh yeah, I'm sure this is true. 64 is indeed less than that. Therefore, 8 squared is less than that. Therefore, 2 is less than that. Therefore, this thing is indeed less than 0. Check. And I could say I've drawn the correct picture. This thing is less than 0. And we have 2 minus 5 root 7 over 4. That is probably entirely alien. And I'm sure it feels weird because I know when I first saw it, it was very weird for me. If you really want, use a calculator. But I'm telling you, this is so valuable to be able to do this. But whatever. Do it however you want for right now, and it's cool. But you do need to check because trust me, you will have problems in your homework where you think, okay, well, the negative one's over, the minus one is over on the negative side, and this is that. And it turns out, no, you actually drew the wrong picture. It actually does something like this and comes through like that. And so, yeah, be careful with that. So that's how we find the X-intercepts. Questions?
No.
So far? No. Okay. So now let's find the Y-intercepts. And let's do that together and let's see what you get. So we are going to find the Y-intercepts right now.
Yeah.
Good. -3 plus or minus. Now, thinking about this, right? Anytime I'm solving for Y, my answer had better be, because I can see it's Y plus something and then squared. So the last thing I'm going to do is have everything on one side and I'm going to take a square root. That's going to give me a plus or minus an answer. Then I'm going to take that, subtract the 3 over. And so my answer should be in the form Y equals negative whatever that is. So Y equals -3 plus or minus some stuff. And that makes sense with my picture when I look at that. This says that, well, if I'd drawn it very well, we'd see like, yeah, you're here at -3. That is the major axis right there. And any vertical line that goes through that is going to have to split that axis. So I should have something in this form, which says that to find the Y values, you go to -3 and then go plus some amount, and then you go minus some amount, and that's how you find those things. And so this is where we're going to use some arrows because this is starting to get really ugly. I'm going to give myself some space and call this one -3 minus 4 root 21 over 5 and put my arrow right there to say that's where that point is. The plus is going to be the higher one. And I don't need to recheck this, right? Like I don't need to make sure that this is positive because I've already checked this one, right? Because the question was at the very beginning, like, I know I have a ellipse and there's 3 scenarios. Either it goes above the origin, it goes through the origin, or it's going to go beneath the origin. And once I find either one of those, right, like I found that it had to go through here, well, then that requires that the other one has to go through here, right? If we had done that work earlier and we found, oh, it was actually a positive number, so it should have gone through here, then I would know that, well, then to continue that point off, it's got to go through there. I don't need to do that work. Conversely, if you had found this point first, you'd say, well, is this number right there in the right place? Is it indeed above the x-axis? In other words, is that Y value positive? And we go through and find, yes, it is. Okay, then I feel confident about that stuff. So finally, we're going to label that point -3 plus 4 root 21 over 5 is that point right there. And it's ugly because there's no way to not make these things really ugly. That's what it's going to look like. Okay. So one way of just getting right to this picture is to, instead of drawing the fake axes first and all that, we could just draw the actual axes, looking at where the shift is, right? Like I know that, you know, looking at this, I could tell, I have this kind of picture in my head that I'm going to have an ellipse right here. That's going to move it 2 units that way. That's going to move it 3 units that way. And so what I could do, I've already found this, I can get rid of this. I could just start by saying, okay, knowing that this is going to go that way and that way, I guess I'm going to draw this a little bit right there. I kind of want my center of my picture to be over in this direction, since we're going 2 units that way and 3 units that way. And so then I could go ahead and just mark where the new center is going to be. And so that's going to be, I guess, step 1 would be draw actual axes. And of course, it wouldn't be good to draw them like this on my page if I know that my thing's down here. So with this first step, you're kind of imagining, where is this thing going to end up? And I want to kind of get a general idea. Well, it's going to be around here somewhere. So that's the picture I want. It's not going to help me to draw it like that. So, okay. Then step 2, find the center. Find new center. Because in this whole context, we understand I have an ellipse. It's been shifted this way and this way. And so my new center must be at +2, -3. And so we're going to go ahead and mark that. We don't need to mark it with a dot. That's just kind of where I'm thinking it's going to be. Okay, and then 3 is going to be to find the 4 vertices. Find the 4 vertices. And we get that by saying, well, and we're kind of moving our picture back in our head saying, well, if this were just this, if this were the original one without all the shifts, then X would be 5 and 5. And so from the center of this guy, I would move 5 in this direction and 5 in this direction. And so from 2, I would go down -5 down here to, let's see, 2, 1, 0, -1, -2, -3. That's a total of 5. So -3. Mark that point. From 2, I go to the right 5 units. 2, 3, 4, 5, 6, 7. So 7. I go over to 7 5 units. Mark that guy. So this is all still step 3. I'm just finding the 4 vertices. From this center point, I need to go up. How far? Well, my original picture says that we go up 4 and down 4. And so we're going to need to go 4 up from 3. I guess, sorry, 4 up from -3. That gives me -3 is 3, and then +1 would be up here at +1. Then from -3 down 4, I guess I would be down at -7. And this is turning out really wonky because, as you can see, I'm kind of leaning over this way. It will help you to do a better job than what I'm doing right here. But this is the general idea, right? We found our 4 vertices. Then once you find your 4 vertices, just draw the figure. But when you do that, right, and again, like, look at how I've drawn this. Which way should this go? You're always going to wonder, well, unless you don't. If the shift were really, really far, you wouldn't need to worry about the origin. But I could tell these things, there's no question about these. That's obvious. This number, since it's the lowest point, it's got to come back up and go and intercept here above -7. This one, since it's the farthest point right, and it's got to go over there to 2, well, it's got to intersect somewhere between 2 and 7. There's no, it's not ambiguous. This is ambiguous because did I draw this weird? is this really, am I that good at this, or have I drawn it wonky? Well, take your best guess. So this is all part of drawing the figure. Taking your best guess, okay? 5, find intercepts. By setting x equal to 0, solving for y, setting y equal to 0, solving for x. And once you've done that, double check your picture. Yeah, buddy. So if I end up with 2 positive x values, I know I've screwed up my picture. If one of these, if this y-intercept were at 0, well, then I know I screwed up my picture. So that's the idea. We want to double check your picture by looking at the intercepts. Does that make sense, what I was saying?
Uh-huh.
Okay. And then there you go. Now you have this really wonky, ugly looking egg thing, but we know everything about it. Now, alternately, you don't have to follow these steps. If you prefer, you could do something like this, just one bit at a time, just like that. The way I like to do it is a little bit weird, especially because, I was like, okay, we're just going to draw this, and then we're going to have a plus this, minus this, and then you're going to add in a plus and a minus, and that could get a little wonky. It might be, at least when you start doing this stuff, might make a lot more sense to just calculate it in your head. Well, 2 plus 5 is 7, and then you just write 7, and that's good right there. Any questions?
I don't think so.
Okay, this is tough stuff. This is very, very tough stuff. And like, you do get intercepts. I don't think we've seen anything that ugly before in this class. I don't think we've ever seen anything as ugly as the intercepts of a ellipse up until now. And they're going to be ugly. That's kind of just part of it. And so, yeah, this is new and crazy in a lot of ways. And you should be struggling with this. This is definitely where we struggle in this class. So I hope this helps. Let's see, as far as the homework is concerned. So the only other thing really is completing the square in order to turn something into this form. And that's, do you have problems with that? Or like, how do you feel about that? Like, we're just going to collect all the X's, collect all the Y's, and then just individually complete the square. And then you end up with something like what we started with, like a 16x squared plus 9y squared equals 144. And then, well, we know how to deal with that. You just get the 144 out of there and try to turn it into this form, although it's not going to be, it's not going to look like that after completing the square. It'll look more like this: 16x plus 3 squared plus 9y minus 2 squared equals 144. But then that's the idea. If we could take that thing and turn it into this type of thing, then we know how to graph it. And so that's what